So in this problem, we're asked to determine the required length of the chord from point A to point C. So we want to know what is the length of AC, so that the 8 kilogram lamp that's hung at point A can be suspended. At point A, we also have a spring that goes from point A to point B, and we're given the spring constant, and we're also given its original length of 0.4 meters. Okay? So, and so the first thing we're going to do to help solve for the length from point A to point C is we're going to first draw our free body diagram. So we have on our free body diagram, we have our weight, which we know is going to be equal to m mass times gravity. So we have 8 kilograms times 9.81 meters per second squared. That's equal to 78.48 newtons. All right. We have our force that goes from point A to point B. All right. So that's along the x and y axes. And then we get the force from point A to point C. Which is 30 degrees. All right. All right. So we have two unknown forces, TAC and FAB. So we can solve for those two unknown forces using our equilibrium equation. So we're going to set our resultant force equal to 0. We know that our resultant force is equal to TAC plus FAB plus our weight. Alright, so we're going to define TAC, FAB, and W as Cartesian vectors. So we'll start with TAC. TAC is going to have x component of negative cosine of 30 degrees times TAC times the unit vector I plus the y component, which is going to be equal to TAC times the sine of 30 degrees times J. All right. FAB. All right. We're gonna has only an x component, so we can just write it as FAB. All right, and then it'll have no y component. All right, and then our weight will have no x component, but it'll have a y component of minus 78.48 newtons. All right. So, with that information, if we sum and we find our resultant force, what we end up getting is we get the x component of our force is FAB minus cosine of 30 degrees, which is radical 3 over 2 times TAC times the unit vector I plus TAC times sine of 30 degrees, which is 1/2 times minus 78.48 newtons times J. So if we look at just the y component force first, so we sum all the forces in the y direction, what we end up from that, what we'll get is we'll get TAC is going to be equal to 2 times 78.48. Alright, so there's just this equation here, and what we end up getting is we get 156.96 newtons. Alright, and then we do the same thing. We sum. Now we can look at the sum of the forces in the x direction and set that equal to 0. So if we do that, we'll get FAB is going to be equal to radical 3 over 2 times TAC, which we just solved for, which was 156.96 newtons. If we do that, we get FAB is equal to 135.93 newtons. All right. So the third part of our problem is we're we know we're going to use Hooke's law to solve for the length from point A to point B. Okay? So we know that the force within a spring, or the force within AB, is equal to the spring constant, which is 300 Newton meters, times the change in length of our spring. So we were given the original length of our spring in the problem statement was 0.04 meters. So what we're looking for now is the current length of our spring, or the length from point A to point B. Right? So, and we know that FAB we solved for was 135.93 newtons. So we can solve for LAB. So we get LAB is going to be equal to 135.93 newtons. Alright, divided by 300 Newton meters plus 0.4 meters. So we're going to end up with 0.8531 meters from point A to point B. What we're going to do now is we're going to look at our original diagram again. So I'm going to scroll up on our page here. Alright, so we know from point A to point B, we just solved for that it was at equilibrium, it was equal to 0.8531 meters. Okay, so what we need to do is we need to determine what is AC. We were given in the original problem statement that point B and point C were hung 2 meters apart along the x-axis. So what we can do is we can draw a point here at point D. Alright, we can calculate that length. So it would just be equal from point A to point D. That would be equal to 2 meters minus 0.8531 meters. So this would be from point A to point D. Alright, so that's going to be equal to 1.14689 meters. Okay. And now that we have one side of our triangle and we have the angle, we can solve for AC. So we're going to bring this down here. So bring this down. Alright. And we can solve for, if we take the cosine of the angle between point A and point D and point A and point C, we know that's going to be equal to the length from AD over the total length from point A to point C. So we can solve for AC. We know it's going to be equal to AD divided by cosine of 30 degrees. So that's going to be the same thing as if we plug all of our numbers in, we'll get from point A to point C, we'll get 1.32432 meters, or if we round to 3 significant figures, we'll get 1.32 meters. So just to recap what we did in our problem, we first drew our free body diagram at point A. Alright, the second thing we did is we applied our equilibrium equation of our resultant force had to be equal to 0. We summed up all of our forces, put them in Cartesian coordinates, and then using the x components and the y components, we solved for our unknown forces. Then we used Hooke's law to solve for the length from point A to point B. And once we had that overall length, we could use that length to solve for one of the sides of our triangle from point A, C, and D. So we were able to solve for AD using the original part of the problem, and then using the 30-degree angle, we could then solve for our length AC. Alright, so that concludes this problem on equilibrium of a particle with a spring.